I want to go back to section 3.1, number 37. This problem worked off of the previous couple of problems, and we had worked number 36, and I had given you an introduction to this particular problem. And the formula that we're working with is the formula here. The Newton's second law, force is equal to mass times the acceleration. And so that derivative of the velocity would give us the so-called acceleration. It says the positive direction is downward, and for this particular motion, this is some kind of cannonball or some type of ball that's being tossed up. So we're going to use this equation. They give us some of the particulars, and I want to say it's number 36, where they tell us that the initial velocity is 300 feet per second. And for number 37, you want to calculate the maximum height attained by, it's a cannonball, must be less than what you got in part B of problem 36. Okay, and we got around 1,400 feet for that one. So let's see if we can calculate that. So we have m dv over dt. It's given to be m times g minus kv. This implies that dv over dt is equal to g minus k over m times v, where they give us that k is equal to 0.00, another zero. Okay, thank you. No, it's 2 zeros. No, it's fine. I get mixed up with those zeros too. So. I think we saw before, oh yeah, number 36 said that the weight is 16 pounds. So we know that the weight is equal to mass times the acceleration due to gravity. So this implies that 16 is equal to 32 times m. And so we get the mass to be 0.5 pounds. And then they also tell us that the initial velocity is 300 feet per second. So I think that's all we need to get started. So dv over dt is equal to, going back to this equation, it's going to be negative 32. Since the so-called downward thrust is said to be positive, so the cannonball is going up. So we start off with negative 32 minus 0.0025 all over 0.5 v. So this implies that we have dv over dt. I'm going to add this velocity to both sides. So this is plus, that's 0.005 times v is equal to negative 32. This is linear, so the integrating factor is e to the integral of 0.005 dt. So this gives us e to the 0.005 t. So the left side, you recall, is automatically the derivative of the product. This is the derivative with respect to time. The derivative of the product of the integrating factor, which is e to the 0.005 t, times the dependent variable, which is v, is equal to that negative 32 times the integrating factor. Multiply the integrating factor on both sides, right? So we integrate both sides there. So we have the integral of the derivative of the product of e to the 0.005 t dt is equal to negative 32 times the integral of e to the 0.005 t dt. So the left side is just that product, e to the 0.005 t times v is equal to, integrating that e to the 0.005 t dt, we use a u du, so let u equal to 0.005 t, and then dt is 0.005 dt. So it's just a ratio once you integrate. So all we have here after the integration is negative 32 divided by 0.005 times e to the 0.005 t plus some constant. Now that 32 divided by 0.005 is 6,400. So we have e to the 0.005 t times v is equal to negative 6,400 times e to the 0.005 t plus c sub 1. We'll divide both sides by that exponential. So we have v is equal to negative 6,400 plus c sub 1 times e to the negative 0.005 t. So the initial velocity is said to be 300 feet per second. Right? So we're going to use that. We can use that to help us solve for c sub 1. So we have the initial velocity, 300 feet per second. So that gives us 300 is equal to negative 6,400 plus c sub 1. E to the 0 is just 1. So this implies that c sub 1, yes, is equal to 6,700. So the equation for the velocity is negative 6,400 plus 6,700 times e to the negative 0.005 t. Well, we're trying to calculate the height. call it S of t, the height at some time t. We want to get that maximum, right? Well, to get this function s, or the position vector, that comes off of the velocity. So if I integrate the velocity, I get the position vector. Right? So s of t is equal to the integral of vt dt, which is the integral of negative 6400 plus 6700 times e to the negative 0.005t dt. So s of t is equal to, yes, negative 6400 t, right? You integrate that e to the negative 0.005 t, that just becomes 1 over the negative 0.005 times e to the negative 0.005 t plus some constant. So this is plus 6700 over negative 0.005 times e to the negative 0.005 t plus that constant. And if you were working that, and you could have everything going perfect, but if you left off that constant, then your answer is garbage. And so again, that constant term is most important. So let's see, that's 6,700 divided by 0.005. So we have S of t is equal to negative 6,400. And this is minus 134. 1, 2, 3, 4, 5, one more 0 times e to the negative 0.005 t plus c sub 2. What to do with c sub 2? We found c sub 1 to be that 6,700, I believe. Yep. What is c sub 2? It's a constant, right? But what does it represent? The initial height. Let's see. Well, that picture there for number 36 says that it's being launched from ground level, right? So the initial height would be 0. So that means that S of 0 is equal to 0. Right? So that means that when t is 0, then the initial height is 0, starting from ground level. So that means that 0 is equal to negative 64 I left off my t there, is that right? Yep. So t, it's going to be 0. Let me put that in there. I need you. Times e to the 0 plus c sub 2. So that implies that c sub 2 is equal to 1, 3, 4, 0, 0, 0, 0. So the equation for the height at whatever time is 1340000 minus 6700t minus 1340000 times e to the negative 0.005t. Well, we can get the height, 64, that's right. Thank you. What do we need to actually get the maximum height? We have the equation. We need what? The time, right? We need t. How would we find time? Okay, we have the derivative, right? That derivative would be that velocity function, right? At the max height, the velocity is 0. All right? Yes. Yeah. The velocity going, look, this ball is going up, it stops just instantaneously, right? Then it shifts back down. So at that particular time, remember that velocity is already the derivative of the position function anyway, right? So you already got that derivative. It's the velocity function. So you set the first derivative equal to 0. That's the same thing as setting the velocity equal to 0. So to find time, to find t, for the height, set v of t equal to 0. And we got v of t, it's this guy right here. So v of t is at negative 6400 plus 6700 times e to the negative 0.005t. If you set him equal to 0, then we end up with this. We get 6700 times e to the negative 0.005t is equal to 6400. So e to the negative 0.005t is equal to 6400 divided by 6700. Take the natural log of both sides and just do a couple of things at one time. Take the natural log of both sides and divide both sides by negative 0.005 and you get t. So t is equal to the natural log of 64 over 67 all over negative 0.005. Calculate that and let me know what you get. .162 seconds. Yes. So now we go back to that height equation. So S of 9.162 is equal to negative 6400 times 9.162 Oh, there it is right there. Say plus 13400 134,000 minus 134,000 times e to the negative 0.005 times 9.162. Okay, you calculate that, and that'll give you the maximum height. And it says that whatever you get, it should be less than that 1400, right? The 1400 for the so-called height was with no air resistance. This you have a little bit of air resistance. So what did you get? Yep. 1363.79 feet. So it is less than the 1406.25 feet that we found for number 36, Part B. Okay. Two of the critical things about that problem, I don't know if you tried to work it, was finding C-SIP1 and C-SIP2. They were critical to the whole working of that particular problem. Okay. All righty. Any questions up until this point? We had professional development yesterday, and we had the dean from Wallace and Dothan to come and speak to us, and he said really good effective teaching is not asking your students if there's any questions and they only have 1 minute left for the class to be over. So I wanted to ask you now if there are any questions and not wait until. Yes, sir. I was just joking. No, I'm just teasing. Yes, sir. Uh-huh. Now you have to use that differential equation. dp over dt is equal to k times p. And so then p is equal to that constant c times e to the kt. Okay. It's the derivative, right? Yes, sir. Yep. Yes, sir. And if you got time after class, we can probably pull it up online and look at it as well.